is Max Bernards, and I will be presenting today on my work with modular and molecular origami. So modeling molecular structures has been well understood for decades. Chemistry and biology teachers commonly have followed stick models or sometimes even balloons to help their students understand the types of shapes and structures that are formed with molecular sets. However, not all possibilities for this type of modeling have been explored to their fullest potential, which is why I came to origami. In order to understand molecular modeling, you first need to understand valence shell electron pair repulsion theory. It's essentially a mathematical way of predicting the types of geometrical shapes that will be exhibited by molecules based solely on the amount of atoms bonded to a central atom. If there are 4 atoms bonded to the central, you get a tetrahedral, and with an interior angle between the 2 atoms about the central one with a 109.5 degree angle. The angle is a very particular thing for those types of molecules because I actually use that angle to help in the construction and the proof of this system later on. I used modular origami for this project because it is a both incredibly versatile and incredibly accurate system for modeling almost any type of molecular, not just molecular, but any type of mathematical structure. It is formed by taking interlocking individual pieces of origami that connect with nothing else but flaps and folds of paper to hold itself together. And it is able to form some immensely complex and amazing structures. And this is ideal for mathematical systems and modeling molecules and their types of structures. 2 previously done types of modular origami that I used principles from, that I included in my construction, is Yoshihide Momotani's carbon module and Tomoko Fuse's method of modeling polyhedra. Momotani's carbon module is excellent for modeling carbons, and that is it. And I saw the principles used from it, but I wanted to expand that type of system to be able to model any other type of molecule, more than just a carbon. I wanted to also be able to do oxygen, nitrogen, and all those other types of molecular bonds. Tomoko Fuse's method is just simply a way of making simple face polyhedra, where you make the individual faces of the shape and then connect it together. My goal was to combine principles from both of these in order to make a new way to construct these molecular shapes in a way that was both accurate and inexpensive, using origami paper. So first, in order to have the proper shapes that I can make using Tomoko Fuse's method, I need to modify the original shapes that are exhibited by those types of molecules. For those last 3 molecules that were shown on the table earlier, we get the tetrahedra, the trigonobipyramid, and the octahedron. However, if I were to just go ahead and model those using Tomoko Fuse's method of polyhedra, in order for me to connect those types of molecules together, I would have to do it vertex to vertex, which is not structurally sound. So I modify those objects by truncating them and obtaining the birectified polyhedra, also known as their dual polyhedra. These dual polyhedra are useful because each of those faces are normal to the legs of its parent polyhedra. Meaning, if you were to draw lines from the vertices of those parent polyhedra to their center, those lines would come at an exact orthogonal or right angle to the faces of each of its dual polyhedra. This is useful because then I can just model those polyhedra using Tomoko Fuse's method, then connect them face to face using some type of connection method. I went through an in-depth process to prove that those polyhedra were the proper ones to use for this method, using some multivariable calculus and vector analysis. I defined each of those shapes as a system of intersecting planes. Doing this gives me a vector normal to each of these planes, and then I can calculate the angle between those vectors. If the angle between each of those vectors is equal to the interior angle of the molecules shown, then this polyhedron will be accurate. And I repeated this process for the tetrahedron, for the triangular prism, and for the cube, and I got 100% accuracy for every single one, thereby proving that these polyhedra were the proper ones to use for this type of molecular model. With the proper polyhedra now found, all I needed was a way to interconnect them. And to do this, I creatively designed what I call the normal connector. It takes either 3 or 4 individual small yellow pieces, shown here, yellow, that connect to either form a triangle or a square, really just depending on what you're wanting to make. The normal connector then attaches to a face made using Tomoko-Fusu's method of polyhedra. Then you form a polyhedra with normal connectors attached to all the faces, and you can make a carbon, or if you were to take away one of those normal connectors, you would have ammonia, or even one more, and you would have H2O. And these types of molecules can then interconnect because of this normal connector. And that bond that forms from that attachment is actually amazingly strong. Through a couple bit of tests, I actually found out that the normal connector, the attachment between the normal connectors was much stronger than the attachment within the polyhedra itself. And it was rather satisfactory to find. The system works incredibly well, and it is accurate. And however, it is rather limited in that it is only able to form single bonds within molecules. I do not, as of now, have a method to model double or triple bonds within molecules, but that would be an excellent way to improve the system. Another good way would be for me to improve the way in which I create the polyhedra so that those would either be quicker or more structurally sound, so that they would be less likely to fall apart.
Questions? Questions from the judges?
Have you considered writing a program or figuring out maybe some way to do this computationally that might be more accurate and less tedious? It seems like that.
3D modeling has definitely been used for this a lot, but I meant to include this. One of the main reasons why this system could be useful is because biology and chemistry teachers could use it as a teaching method, and it would be extremely useful for having their students actually make these pieces and then understand the types of shapes that these molecules form. So a bunch of teachers, so have the students make all the individual pieces and then put it together and you get these molecules. And in particular, for teachers in areas with less funding or are not able to get those types of plastic balls sets, and it's hard for them to help their students understand this type of modeling, they can just use paper and then make it themselves, and then the students will be able to understand these types of principles really well. So the 3D modeling using programming is possible. It's not exactly in my skill set currently, but that's something that is definitely possible. You have a question?
Was this your original idea? Is it something that just happened? You were bored?
I go to the
Origami, and then you said, oh, I can make a model kit.
I go to the Arkansas Math and Science School down in Hot Springs, and we are seniors do what is called the Fundamentals and Research Method project, where they spend about a year and a half working on a in-depth project, and either teachers can give prompts for the students to work on, or students are allowed to propose their own ideas. And I knew that I wanted to do something with origami. I didn't figure it out until the firm idea happened. I actually do origami as a hobby and have done it for quite a long time, since I was maybe like 8 or 9. And being able to construct and do something as in-depth as this with one of my favorite hobbies was definitely part of the drive to create this system. It was a combination of I want to do something with origami, and I also want to do something unique. And so I thought maybe I could just figure out a way to model these types of structures. And I did a lot of looking at Moatani's carbon module was the only thing I previously found that was of origami that was used for modeling.
students need to have in order to produce something that was, you might call accurate?
The thing that I made sure to do is make sure this origami was simple. All you need to do is make sure that the proportions between the pieces of paper are right. When you're making the triangular or the square pieces of paper, the connectors need to be a third of the size of those pieces. And besides that, the step-by-step process is really
All right, well,
easy.
get this thing up on the web for us.
That was actually my plan. Once I figure out a way to make double or triple bonds, I'm going to make it into instruction and make it available to teachers.
Is this something that could be used in a classroom setting where a lot of kids could each be assigned to make the individual components and then put it all together?
Easily. And that would actually make it much quicker because that's definitely one of the setbacks about this is it's a lot of individual interconnecting pieces. And in order to make more complex structures, you need to make a lot of the pieces. And so it can be time consuming, but if you have people working